This is the problem that we are given. We are provided with a unit square. Let me just draw it parallelly with you. So we have a unit square, and there's this triangle inside the unit square. Here we go. From PC, we have the triangle. This is the unit square. All right. We've, we are provided with points P and Q. We have to find this angle. Let's call this theta. The theta looks weird. Okay. All right. And we are also provided that the perimeter of triangle QAP is 2 units. We are supposed to find angle PCQ. While this is a unit square, so this length is of course 1. Now let's say this length AP is A and this is B. This of course is 90 degrees. Now if you try to spot some congruent triangles in this diagram, it's not very easy. You see, apart from this middle triangle, every other of them has a right angle triangle. And we are not really sure about these two angles. It's very difficult to spot a congruent triangle from these. So what we'll do is, we'll use the technique of rotation. Why? Because it's not easy straight away to spot congruent triangles. So what we'll do is, we'll force congruency. And how are we going to rotate this? We'll rotate what? We'll rotate triangle QCD. Alright. So I'll have to make you visualize how exactly do we do the rotation through this problem. So let me just bring the diagram down. Alright. Perfect. So we intend to rotate triangle CQD. CQD. Right. So instead of looking at the whole figure, I recommend you to look at the parts of it. What are the parts of it? We have side CQ, side CD, and DQ. Look at the diagram in parts. Let's say this angle is alpha, this angle is beta. We're rotating this triangle. So first of all, let's look at CD, this side. So let's say we have to rotate it by 90 degrees. So we'll rotate CD by 90 degrees. So I'll make a perpendicular. That will be the new position of CD. Let's call this D1. D got there, right? Now let's come to CQ. CQ. We'll rotate CQ by 90 degrees as well. We have to rotate the whole diagram by 90s. So CQ by 90, I'll drop a perpendicular on CQ. Yes, and this will be the new position of CQ, the Q1, and we have D1 Q1 as the new position of DQ. Perfect. Now once again, we need to rotate it by 90 degrees. What our intention is, we have to make CD coincide with BC. CD coincide with BC. We have to turn this whole thing and bring it here. So once again by 90 degrees, we'll have something like this. Perfect. And once again, if we do by 90 degrees, we'll have this diagram. So this is what we need. This is the final position of what? Of Q, Q3, and D came here, coincided with B. Now, let me just change the color. I want you to look at two triangles. I want you to look at this triangle, this, and this. What are we calling them? CQP and CPQ3. Yep. Notice that CP and CP are common. This thing, right? Also notice that CQ, this is the triangle that we brought here, right? So CQ is basically this. CQ3 is the new position for CQ only. So this equals this. Now we have S and S. What criteria can we have? Either we can have SAS or triple S. We don't really have much data regarding the angles here. So we'll stick to this. We'll have to focus on this one. What side do we have now? We have PQ and PQ3. Perfect. That is what we are supposed to make equal. Now if you focus on PQ, what do we have? Do we have any data regarding this triangle? The perimeter is provided to be what? 2. These sides are A and B. So PQ would be what? 2 minus A plus B. Now look at PD. PD, that is 1 minus A. And also look at DQ3. What is DQ3? DQ3 is basically the new position of DQ, because this is what we rotated here. DQ came back here. So DQ3 would be equal to what? DQ, and DQ is what? 1 minus B. Also notice that PQ3, this side that we are supposed to find, is what? PD plus DQ3, that is 2 minus A plus B as well. So we have these two sides equal as well. Perfect. Now we have triangle. Let me just once again shift the diagram. Alright, so we have triangle CPQ equals to triangle CPQ3. Perfect. This triangle equals to this triangle. Now, what do we do when we have two triangles congruent? We collect the treasures using CPCT, the corresponding parts. Can we say angle PCQ3 equals angle PCQ? Right? What is angle PCQ? That is theta. Also notice that since this is the same triangle as this, because this has been rotated here, so this angle is also alpha. The same angle is here, right? So we are essentially saying that alpha plus beta equals to theta. Notice from the square that alpha plus beta plus theta is what? 90 degrees. Now these two equations we have, from these two, what can we say? We can put theta in place of alpha plus beta. So we have 2 theta equals 90 degrees and theta to be 45. That's our answer. Perfect. Now a lot of people must be like really confused, like people were in the live class. How does one even think of something like this, something this absurd, like rotating this and then forcing a congruency and then coming up with the answer? You don't like, a beginner is not able to think something like that. Of course, if you are able to think and you are a beginner, you're not normal. All right, a normal human cannot think of this. So what we do coordinate geometry. All right, so that will be our approach 2 for this problem. I won't be solving the whole thing using coordinate geometry. I'll just give you the hint for those who don't understand how we exploit coordinate geometry in synthetic geometry problems. I'll just shift the diagram. Perfect. So what we'll do is we'll assume the coordinates of this point for our convenience as 0 0. That means we'll assume that this is the origin. Remember that this distance was a, so let me just mark this a and this as b. So point P, the coordinates of point P is going to be a0, and of point B is going to be 1 0, right? Ignore this part now. We don't have to look at this. We have to look only at the square, the original diagram. And for this, it's going to be 0b and 0 1 here, and for C it will be 1 1. Perfect. Now what do we have to do? We have to find theta. What is theta? Theta is the angle between two lines. What are the two lines? CQ and CP. Have you studied something like this in straight line? For people who have studied straight line. For those who don't know straight lines, the angle between two lines, if theta is the angle between two straight lines, then tan theta is given as m1 modulus of m1 minus m2 upon 1 plus m1 m2. Now what is m1 and m2? M1 is slope of any one of the lines, let's say of CQ, and m2 is also the slope of CP. Now what is the slope? Let's say this is a line AB. Coordinates of point A are x1, y1. Coordinate of point B, x2, y2. So we have slope of AB, MAB, let's say, that would be y2 minus y1 by x2 minus x1. Notice that we have the coordinates of the edges, like the vertices C and P, A0 and 1, 1, 1, 1 and 0, P. So we can find the equation from here. Now it won't be a very sweet looking equation. So we'll have to use one more condition. What's the condition? The perimeter one. The perimeter of triangle QAB was provided to be 2. We said that side QP is 2 minus, alright, 2 minus A plus B. We can also find the length of QP if you observe this triangle. This is a right angle triangle using the Pythagoras theorem. So I'll be doing exactly that. So I'll be writing 2 minus A plus B is also equals to what? Under root A square plus B square. Now I'll square both sides. I'll have this 2 square minus plus A plus B the whole square minus 2 into 2 into A plus B. So when you solve this, you'll get an equation which looks like a Diophantine equation, and it looks like very sweet. It looks like you can factorize it using the Simon's favorite factoring trick, but that won't really help. I tried to use Diophantine. It won't help because A and B are not integral. Alright, so don't waste your time on that. Use it on the tan theta equation that we had earlier from the equation of straight lines. And when you do that, you'll realize tan theta comes out to be 1 and theta will be what? 45 degrees. So that is how you exploit